Welcome to Tech Girl Kannada YouTube channel.
Electrical conductivity in metals. Review of classical free electron theory. Failures of classical free electron theory. Assumptions of quantum free electron theory. Density of states. Fermi energy at 0 Kelvin derivation. Fermi factor. Variation of Fermi factor with temperature and energy. Mention the expression for electrical conductivity. Success of quantum free electron theory. Numerical problems. A review of classical free electron theory. This theory was proposed by Paul Drude and later improved by Lorentz to explain electrical conductivity in metals. According to this theory, metals consist of free electrons, and the expression of electrical conductivity is given by sigma is equal to Ne square tau by m, where N is the free electron concentration, E is the charge in the electron, tau the relaxation time of free electrons, and m is the mass of the free electrons. Failures of classical free electron theory. Classical free electron theory has successfully explained electrical and thermal conductivities in metals, but failed to account for specific heat, dependence of electrical conductivity on temperature, and electron concentration. Specific heat. The molar specific heat of a gas at constant volume Cv is equal to 3 by 2 R. Since free electrons are expected to behave like gas molecules as per free electron theory, the above formula is applicable for free electrons as well. However, the contribution of free electrons to the specific heat of a metal has been experimentally found to be Cv is equals to 10 power minus 4 RT. Thus, it is experimentally found that specific heat depends on temperature and is far lower than expected value. Temperature dependence of electrical conductivity. It has been experimentally observed that electrical conductivity of a metal is inversely proportional to the temperature. Sigma experimental is directly inversely proportional to the temperature. But according to the assumptions of classical theory, electrical conductivity of a metal is inversely proportional to the square root of its temperature. Thus, the prediction of the classical free electron theory doesn't agree with the experimental observations. Dependence of electrical conductivity on electron concentration. As per classical free electron theory, the electrical conductivity is given by sigma is equal to Ne square tau by m, which implies sigma is directly proportional to n, where n is the electron concentration. Therefore, as per the above relation, those metals which have high electron concentration must have high electrical conductivity, sigma. But in reality, it is not so as per the experimental data given in the table. In other words, zinc and cadmium must be good conductors on account of their high value of N when compared to copper and silver. But copper and silver are found to be better conductors compared to zinc and cadmium. Metals, valency, and sigma conductivity. N is the electron concentration. Copper, 1 valency, 5.88 into 10 power 7 ohm meter. Concentration is 8.54 into 10 power 28 per meter cube. Silver 1 6.30 into 10 power 7, 5.85 into 10 power 28. Zinc 2 1.09 into 10 power 7, 13.10 into 10 power 28. Cadmium 2 0.15 into 10 power 7, 9.28 into 10 power 28. Quantum free electron theory. Quantum free electron theory was proposed by Arnold Sommerfeld in 1928, in which he retained the vital features of classical free electron theory and included Pauli's exclusion principle and Fermi-Dirac statistics. It is successful in explaining the low specific heat value of conduction electrons, the correct dependence of sigma on T, and correct expression for electrical conductivity in terms of Fermi velocity. Assumptions of quantum free electron theory. The energy values of conduction electrons are quantized. The allowed energy values are realized in terms of a set of energy levels. The distribution of electrons in various allowed energy levels occurs as per Pauli's exclusion principle. Free electrons in a metal travel a constant potential but stay confined within its boundaries. The attraction between free electrons and lattice ions and the repulsion between the electrons themselves are ignored. The energy values of conduction electrons are quantized. The allowed energy values are realized in terms of a set of energy levels. The distribution of electrons in various allowed energy levels occurs as per Pauli's exclusion principle. Free electrons in a metal travel at constant potential but stay confined within its boundaries. The attraction between the free electrons and lattice ions and the repulsion between the electrons themselves are ignored. Density of states. The permitted energy levels for electrons in a solid material will be in terms of bands. Each band comprises of a huge number of permitted energy levels which are not evenly distributed. Each energy level corresponds to one energy value, and each energy value is applicable to two electron energy states. One for an electron with spin up and the other one for an electron with spin down. Thus, we find a large number of electron energy states even in a small energy range. The number of available energy states per unit volume per unit energy range at a certain energy level is called density of states and is represented by G of E. Density of states G of E. G of E dE is equal to 8 root 2 pi m power 3 by 2 by h cube into e power 1 by 2 dE, where dE is an infinitesimally small increment at an arbitrary energy value E. In a band, m is the mass of electron and h is Planck's constant. E, E1, E2, dE. Fermi energy. Consider a conductor containing n free electrons at absolute zero temperature. These electrons fill the available energy state starting from the lowest energy level, from the bottom of the band, according to Pauli's exclusion principle. So, below a particular energy level, all the energy levels are completely filled, and once above it will remain completely vacant. The energy corresponding to the highest occupied energy level. The energy corresponding to the highest occupied energy level at absolute zero temperature is called Fermi energy. And the highest occupied energy level is called Fermi level. Fermi energy at 0 Kelvin is denoted by EF naught and is written as EF naught is equal to h squared by 8m 3n by pi whole power 2 by 3 h squared by 8m 3n by pi whole power 2 by 3, where m is mass of electrons, n is free electron concentration, and h is Planck's constant. For all practical purposes, Fermi energy at any temperature T is taken as Fermi energy at 0 Kelvin, EF not itself, except at extremely high temperature. Expression for Fermi energy at 0 Kelvin. Filled energy level, vacant energy level, T is equals to 0, EF energy. Let G of E be the density of states. The number of energy states in the range of E and E plus dE is given by G of E dE. Let N of E dE be the number of electrons per unit volume which have energy in range of E and E plus dE. N of E dE equals to number of available energy states in the range E and E plus dE into probability of occupation of these levels by electrons. But the probability of occupation of energy states by electrons is given by Fermi factor. So N of E dE is equal to G of E dE into F of E. Now we need the number of electrons per unit volume of a metal, which have got the energy from E is equals to 0 to E is equals to E max. Maximum energy possessed by electrons, it is represented by N and evaluated by integrating equation 1 from E is equals to 0 to E max. N is equals to E 0 to E max. N of E d is equal to E is equals to 0 to E max. G of E F of E d. But F of E is equals to 1 at T is equals to 0 Kelvin. But F of E is equals to 1 at T is equals to 0 Kelvin. We know that G of E d is equals to 8 root 2 pi m power 3 by 2 by h cube into e power 1 by 2 dE, where m and h are mass of the electron and Planck's constant respectively. N is equals to 8 root 2 pi m power 3 by 2 by h cube
E0 to E max e power 1 by 2 dE is equal to 8 root 2 pi m power 3 by 2 by h cube into 2 by 3 e power 3 by 2, 0 to E max. But at T is equals to 0 Kelvin, the maximum energy that any electron of the material can have is EF naught. Hence, E max is equal to EF naught. Next, n is equals to 8 root 2 pi m power 3 by 2 by h cube into 2 by 3 EF naught power 3 by 2 is equal to 8 into 2 power 3 by 2 m power 3 by 2 by h cube into pi by 3 EF naught whole power 3 by 2. EF naught power 3 by 2 is equals to h cube by 8m whole power 3 by 2 3n by pi, or EF naught is equal to h square by 8m 3n by pi whole power 2 by 3. Fermi factor. What is this Fermi factor? When a metal reaches an ordinary temperature starting from absolute zero temperature, electrons near Fermi level can take up the thermal energy and reach unoccupied levels. This kind of distribution of electrons in various energy levels is systematic in nature and is governed by a statistical function once the system is in thermal equilibrium, steady temperature state. The probability that a given energy with energy E is occupied at a steady temperature T is represented by F of E and is called Fermi factor. First, the Fermi factor is defined as the probability of occupation of the given energy state for a material in thermal equilibrium. Fermi factor is defined as the probability of occupation of the given energy state for a material in thermal equilibrium. It is given by F of E is equals to 1 by E power E minus EF by KT plus 1. Variation of Fermi factor with temperature and energy. Variation of Fermi factor with temperature and energy can be understood by considering three different cases of probability of occupation as follows. At T is equals to 0 Kelvin and E is less than EF. At T is equals to 0 Kelvin and E is less than EF. When T is equals to 0 Kelvin and E is less than EF, the Fermi factor can be written as follows. F of E is equals to 1 by E power minus infinity plus 1. E power minus infinity is 0, 0 plus 1 is 1 and equal to 1. Which means all the energy levels below Fermi level are completely occupied at T is equals to 0 Kelvin. At T is equals to 0, but E is greater than EF. F of E is equal to 1 by E power infinity plus 1 by infinity is 0. Which means all the energy levels above the Fermi level are unoccupied at T is equals to 0 Kelvin. At T is greater than 0, ordinary temperature, and E is equal to EF, F of E is equals to 1 by E minus EF by KT. E is equal to EF, right? E is equal to EF. So E minus EF is 0. E power 0 is 1. 1 by 1 plus 1 is equals to 1 by 2, which means the probability of occupation of Fermi level at ordinary temperature is 50%. It is also clear from the below diagram that the value of probability remains 1 for E is very much lesser than EF at ordinary temperature and starts decreasing from 1 as the value of E becomes closer to EF. Further, the probability value falls off to 0 rapidly when E is greater than EF. That is shown in this figure. E, this is probability of occupation of various energy states for a material at thermal equilibrium versus energy level. electrons, and this can be taken as 0 probability to 0, 0.5 to 1, and when t is equals to 0, the probability will be 1, and the same thing when E is less than EF, t is equals to 0, the probability is 1. When E is greater than EF, when t is equals to 0, the probability is 0. When t is greater than 0 Kelvin, E is equal to EF, that time the probability will become 50%. Fermi factor. The Fermi factor of electrons which occupy Fermi level. The Fermi velocity. The velocity of electrons which occupy Fermi level is called Fermi velocity and is represented by Vf. If Ef is energy of electrons in Fermi level, then Ef is equals to half mvf square. Vf is equals to root 2e by m. Ef is equals to half mv square. Vf is equals to root 2e by m. Fermi temperature. Fermi temperature, Tf, is the temperature at which the average thermal energy of free electrons in a salt becomes equal to the Fermi energy at 0 Kelvin. Average thermal energy of free electrons in a solid becomes equal to the Fermi energy at 0 Kelvin. Fermi temperature is the temperature at which the average thermal energy of the free electron in solid state becomes equal to the Fermi energy at 0 Kelvin. That is KTF is equals to EF, or EF naught is equals to KTF. But for all practical purposes, EF is similar to EF naught is similar to EF. So KTF is equals to EF. TF is equals to EF by K. EF by K. Expression for electrical conductivity. Sommerfeld suggested the following equation for electrical conductivity. Based on quantum free electron theory, n is equal to 8 root 2 sigma is equal to ne square lambda by mvf, where m is the effective mass of the electron, lambda is mean free path, vf is Fermi velocity, n is the number of electrons per unit volume, and E is a charge. Sigma is equals to ne square tau, or ne square lambda by mv. Success of quantum free electron theory. Merits. Specific heat. As per classical free electron theory, the specific heat of conduction electrons are large, as all conduction electrons are capable of absorbing heat energy at once. But as per quantum free electron theory, only those electrons that occupy energy levels close to the EF can absorb heat energy, and such electrons are very small in number, hence the specific heat is very low. Also, specific heat is based on the quantum free electron theory is given by the equation Cv is equals to 10 power minus 4 RT, which is an agreement with the experimentally observed values. Thus, quantum free electron theory successfully explained the low specific heat of conduction electrons. Temperature dependence of electrical conductivity. It has been experimentally observed that the electrical conductivity of a metal is inversely proportional to its temperature. That is, sigma experiment is inversely proportional to the temperature. As per quantum free electron theory, the electrical conductivity of metals is given by sigma is equal to ne square lambda by mvf. Sigma is directly proportional to lambda. Sigma is equal to ne square lambda by mvf. Sigma is directly proportional to lambda. The waves associated with electrons suffer scattering by vibrating lattice ions while moving in a conductor. These vibrating ions can be considered to be present effectively in a cross-sectional area by r square, where the r radius can be considered to be amplitude of vibrations, and the vibrations of larger area of cross-section cause greater scattering of waves. The increased scattering of waves results in reduction in mean free path lambda. Lambda is equals to 1 by pi r square. But the amplitude r of vibrations is proportional to thermal energy, which in turn is proportional to temperature T. R square is directly proportional to T. Comparing 2 and 3, we get lambda is inversely proportional to T. Comparing the relation 1 and 4, we get sigma is inversely proportional to T. The quantum free electron theory successfully explained the relation between conductivity and temperature. Electrical conductivity and electron concentration. According to quantum free electron theory, the conductivity of conductor is given by sigma is equal to Ne square lambda by m Vf. Thus, the conductivity depends on the number of electrons per unit volume, n, as well as the ratio of lambda by Vf and m star. If we compare the cases of copper and aluminium, the value of lambda by Vf for copper is about 3.73 times higher than that of the aluminium. Also, the value of m star for aluminium is 1.08 times that of copper. Thus, the copper has higher conductivity compared to aluminium.
Thank you for watching. Do like, share, and subscribe to my channel.